does heat travel? Heat can be transferred from one place to another by three methods. We have conduction in solids, convection of fluids for liquid or gases, and radiation through anything that will allow radiation to pass. The method used to transfer heat is usually the one that is the most efficient. If there's a temperature difference in a system, heat will always move from higher to lower temperatures. Conduction occurs when two objects at different temperatures are in contact with each other. Heat flows from the warmer to the cooler object until they are both at the same temperature. Metals are very good conductors of heat, while air is very poor. You experience heat transfer by conduction whenever you touch something that is hotter or colder than your skin. Example is when you wash your hands in warm or cold water. The next image shows a thermal infrared of a coffee cup filled with a hot liquid. Notice the rings of color showing heat traveling from the hot liquid through the metal cup. You can see this in the metal spoon as well. This is a good example of conductor.
Now, let's try to solve a sample problem. Determine the rate of heat transfer by conduction per unit area. The means of conduction for furnace well made of fire clay. Furnace well thickness is 6 inches or a half a foot. Thermal conductivity of the furnace well clay is 0.3 watts per meter Kelvin. The furnace well temperature can be the same as furnace operating temperature, which is 650 degrees Celsius, and temperature of outer of the furnace is 150 degrees Celsius.
In conduction, heat transfer rate is expressed by the coefficient of conductivity multiplied by the area times the change of temperature per length. So for this given sample problem, our given temperatures are at 650 degrees Celsius and 150 degrees Celsius. And for the given length of 12 inches, we need to convert it into meter. So let's multiply 12 by 0.0254 meter, and that will give us 0.3048 meter. And for our given coefficient of conductivity, that is equals to 0.3 watts per meter Kelvin. So the solution in this sample problem is quite straightforward as demonstrated in this video. So now let's calculate the heat transfer rate per unit area of the wall. So that is Q over A equals to the coefficient of conductivity multiplied by the change of temperature per length. So let's plug in all the given parameters. So for our coefficient, that is 0.3 watts per meter Kelvin multiplied by the change of temperature, that is 650 minus 150, and we can use Kelvin for that, over the length of 0.3048 watts per meter. Now let's calculate, and that will give us 492.13 watts per meter squared. Now let's go to convection. In liquids and gases, convection is usually the most efficient way to transfer heat. It occurs when warmer areas of a liquid or gas rise to cooler areas in the liquid or gas. As this happens, cooler liquid or gas takes the place of the warmer areas which have risen higher. This cycle results in a continuous circulation pattern and heat is transferred to cooler areas. You see convection when you boil water in a pan. The bubbles of water that rise are the hotter parts of the water rising to the cooler area of water at the top of the pan. You probably heard the expression, hot air rises and cool air falls to take its place. This is a description of convection in our atmosphere. Heat energy is transferred by the circulation of the air. Now let's take an example. Hot air is at a temperature of 150 degrees Celsius flows over a flat plate maintained at a water temperature of 50 degrees Celsius. The forced convective heat transfer coefficient is at 75 watts per meter squared degrees Celsius. Now let's calculate the heat transfer rate into the plate through an area of 2 meters squared. So let's assume that this is on a steady state condition. So first, let's write in the temperature of the fluid of the hot air, which is 150 degrees Celsius, and for the water temperature of 50 degrees Celsius. And of course, our given coefficient of convectivity, that's 75 watts per meter squared Kelvin, and for the area of 2 meters squared. So let's find the rate of the heat transfer for convection, and that is H for our unknown. So for our given formula of convection, we have the heat current equals to the coefficient of convectivity multiplied by the area times the change of temperature of our fluids. So we'll plug in the given parameters of 75 watts per meter squared Kelvin for our convectivity, multiplied by the area of 2 meters squared times the change of temperature. That's 50 minus 150 Kelvin, and we can simply use 15 kilowatts for the transfer rate into the plate. Finally, let's talk about radiation. Both conduction and convection require matter to transfer heat. Radiation is a method of heat transfer that does not rely upon any contact between the heat source and the heated object. For example, we feel the heat from the sun even though we are not touching it. Heat can be transmitted through empty space by thermal radiation. Thermal radiation, or often called infrared radiation, is a type of electromagnetic radiation or simply light. Radiation is a form of energy transport consisting of electromagnetic waves traveling at the speed of light. No mass is exchanged and no medium is required. Our last example, an astronaut is at work in the service bay of a spacecraft and is surrounded by walls at -100 degrees Celsius. Outer surface area of the suit is 3 meters squared and aluminized with an emissivity of 0.05. Let's calculate the rate of heat loss when the suit's outer temperature is at 0 degrees Celsius. And now let's solve it. So for a given temperature of the suit, that's -100 degrees Celsius, so we need to convert that to Kelvin, and that's 173 Kelvin. And for the outer suit temperature of 0 degrees Celsius, that's 273 Kelvin. And for the emissivity, that's 0.05, and the area of 3 meters squared. And according to Stefan Boltzmann law, the heat radiated depends on the surface once emissivity is known. So basically, the given formula for radiation is the heat current equals to the emissivity multiplied by the coefficient and the area, and for the temperatures must be raised to 4. So now let's plug in all the given parameters. For the emissivity, that's 0.05 multiplied by the area of 3 meters squared, and the coefficient, which is constant, that's 5.67 by 10 raised to -8 watts per meter squared Kelvin raised to 4, multiplied by the given temperatures. And again, that should be in Kelvin and should be raised to 4 as well. So basically, our final answer is at 39.6 watts.